remembrance our God. Al-Fatiha. Okay, we have gone to the introduction of the elastic plastic bending. Okay, so just remind us again. In this, there's a lot of way to deal with this, but we are going to assume that the material behave. Okay? We're going to assume that the material behave like this. Yeah? Elastic, perfectly plastic. So this is sigma y. Yeah, the stress and strain. So this is the theory. The material behave in elastic, perfectly plastic. Elastic here, and then perfectly plastic. That means constant plastic. Sigma y. So those are the material behavior for our theory. So how can we go back to analyze how to calculate the work, how to calculate the force to make it bend. So simple case, this one is a very simple case here. Put a beam there, push in the middle there. Want to push in the middle, at the end of the day, they bend like that. Yeah? So this is the place. Here there is a place where the bending is happening. So they must have gone into plastic. They must gone into here, somewhere here. Not just in elastic cases. Yeah? So how much is the moment required, or how much the force required for it to bend? Those what we want to study. So those are very simple cases. Sometimes this point here, it's not in the middle. Somewhere there. Yeah? Maybe 2 meter, 1 meter there. So the bending is like that. Sometimes we put it in a built in there, push load there. So it bend like that. Yeah, it bend like that. So the bending happen there. Because those are the highest moment. Here the bending happen in there. Because those are the highest moment. They have a moment there, but the highest moment there. So whatever happening, the highest moment will be happening there. All the hinge of the bending will be happening there at the highest moment. So those are the main point that we have to understand. And then how to calculate that force. How much force we want to push. Before we want to calculate the force, we have to calculate the moment required. Before we want to calculate the force, we have to calculate the moment required. What are the moment required? So, let's say the cross section of the beam is like this. 40 mm times 100 mm. So these are the beam cross section. So the beam has a material like this. The sigma y is 200 megapascal. Everybody, are you with me? So we want to study this case. These are the properties of the material, and these are the size of the beam, the cross section. The beam cross section, 40 times 100 mm. So what do you want to do it? What we want to do it? Case 1. Case 1, we want to calculate what is the moment required for it to start plastic. To start plastic mean what? The surface here, the top and bottom here, the stress mass equal to the yield stress. So we call it moment maximum elastic. Some people call it maximum elastic. This is equal to moment start of plastic. So both of these definitions are the same definition. This is plastic, but this is the starting of plastic. This is elastic. So those are the maximum point of elastic, the same point. Start of plastic or maximum elastic, they refer to the same point. So in this case, we just use one term. The definition we want to use is maximum elastic. Moment maximum elastic. ME, maximum elastic. And then, so this is the diagram here. The diagram here, the stress diagram side by side. So the stress here must be sigma y. And then straight line there, the stress here must be sigma y. This must be 200. Only one layer here is plastic. What is plastic? The stress there is 200. If the case, the yield is 300, so the stress is 300. For this case, the yield is 200. So the stress is 200. The other is less than 200. Less than 200. So this is the diagram of the stress. So, can we calculate the moment required for this to happen? Yes. What do we do? What's the last time? What do we use?
We use the FD.
Summation of force time distance. Sum total of force time distance. What is the force there? So this is the stress here, this is the center there. So this triangle here act on that area. So it will create a force. The force must be at the centroid. F1 there. So the distance from here to here, call it D1. So that is 100. So this is 50. So this is 50. This is 50. Yeah? This is 40. So again, from this diagram, we can calculate straight away. Okay, put aside there. We can calculate straight away. What is F1? This is F2 there. F2 is going to that side. This is D2. Because the stress is tensile, this is compression. Going to the other side. So what is F1? What is the formula?
Sigma AVG times area.
Sigma average
times area.
Area. Where does area happen? So the sigma average is, the top here is 200, here is 0. So 200 plus 0 divided by 2. That's why you call average. And then the area, this X here is on that area there. What is the area there? 40 times 50. 40 times 50. This is mega. This is milli, and milli become micro. So cancel out mega and macro. The answer must be Newton. What is the value there?
200 kilo.
200, 0, right? So 0, 0, 0. So we change it to 200 kilonewton. First must be Newton there. See that? Because mega and milli cancel out, the answer must be in Newton first. Write it down first. And then you write another one, 200 kilonewton there. Are you with me, guys?
Yes.
And then, what is D1 there? D1, what is the value of D1 there?
2/3 of 50.
2/3 of, that's 50. So 2/3 is 1/3 there. 1/3, 2/3. So this 2/3. So 2/3 of 50. So we have 100 divided by 3. 33.333. Yeah? So, and what is F2? F2 is also the same. 200 and 0. So it's also 200 kilonewton. What is D2? D2 here, the distance to that axis. Okay, if you look from here, the axis is like that. So bending that way, the force that way, moment that way, this moment that way, that's why it add up. And look like that, that's the axis. Look from the front, the axis is like that. Look from the side, the axis is still like that. Yeah? So D2 is also 2/3. So 2/3 from 50. So if we write it back, what is the moment maximum elastic. That means moment, this thing to happen, we require the moment to have a certain value. We can calculate. I don't know the loading yet. This is just, I know the size and the properties. I don't know about the loading yet. How does it load? I don't know. Just the cross-section size and the material properties, I can estimate, I can find what is the required moment. So what is the moment there? Moment maximum elastic is F1 times D1 plus F2 times D2 is equal to F1 times D1 times 2 because symmetry. So what is the value there?
I got 13.33 kilo Newton meter.
Again, what?
13.33 kilo Newton meter.
13.
Am I correct?
The others?
Same.
So 13.33
Kilo Newton
kilo
meter.
Newton meter. So I write 3,333.3 Newton meter. Okay, the moment is 13,000 Newton meter. Okay, clear guys? Clear guys?
Clear.
Okay. Now, what if I increase the moment is higher than this? What happening to the diagram here? The diagram here must be written, and then you can calculate. This is, I know that my force or my moment must be higher than this. Only then I can make a product. Below than this, there's no bending. The permanent bending, the permanent deformation will not happen. It's going back to the original shape. Elastic must be higher than this. So let us try. I want it because I can increase a lot of things. I can make this one 5 mm plastic, 5 mm plastic, 10 mm plastic, 10 mm plastic, 20 mm plastic, 20 mm plastic, 30 mm plastic, 30 mm. There's a lot until 50-50. That is fully plastic. So that from 1 mm until 49 mm, those are all separa plastic. What is the definition? Separa plastic. So we must work in the separa plastic cases. Yeah? So we just draw. How much plastic do you want? Let's say I want it to be, this is 40, this is 50. Yeah, I want it to be 10 mm plastic. 10. So that means 40 there, 10 mm plastic, 10 there, 40 there. So this is also 40. So beside of that, we have to draw the stress diagram. How does the stress diagram look like? So this is start of plastic. This is already long time plastic. So this point here must have sigma y value. So must have 200. So this one is also maintained at 200. That's why 200 also. But this one is still elastic until you reach that point. Until that point, then straight down. Why straight down? Because the value is constant at 200. So this is sigma y, this is also sigma y. Are you with me there?
Yes.
Combination this and that will create a stress. The stress will create a force. So what are the stress? We have to find the force first. So that stress here, 200, 200 here, 200, 200, 200, 200, everywhere is 200. So what? There must be a force. So the force must be at the center, not two-thirds anymore. The center of rectangular here, there must be F1. That F1 will create a moment up to the one. There must be a distant one. And then the triangle here, 200 here, and 0 here. That stress here will create a force there at the center of that triangle. This is center of square. So triangle, there must be F2. And then will be rotate to the axis, must be a distance, D2. Same thing there. There must be F3 there. There must be F4 there. And D3 there. And D4 there. Are you with me, guys?
Yes.
So symmetry there, we just calculate one side. So slowly write down. One is F1. F1 is sigma average times area. What are the average? 200 here, 200 down there. So the average must also be 200. So it must be 200 plus 200 divided by 2. So the average is also 200. What are the area? The area is that one. So 40 times 10. 40 times 10. This is a 40 times 10. Milli cancel out with this mega. So what is the value there?
80,000 Newton.
80,000 Newton. And then write down
80
80 kilo Newton. And then what is your D2? D1 first. See that? How to write this one, distance here? So we write, the distance is there. We write this 40. We know that 40 plus. So this one must be half of 10. You see that?
Yes.
Never write 45 straight away. The working procedure must be shown here. Are you with me?
Yes.
Never do the calculation in your head. Do the calculation on your paper. 40 plus half of 10. So the answer is 45 mm. So what is F2? F2 here. Sigma average. Always write the formula. Sigma average times area. So what are the average there? 200 here and 0 there. 200 plus 0 divided by 2. And then times the area. The area is 40 times 40. So those are the area. Okay, 40 times 40. So what is the value there?
$160,000. Newton.
So it's equal to 160 kilo Newton. So what is the D2? What is the D2 there?
2/3 of 40.
So everything is clear there. Okay? Only then you calculate. What is the moment there? The moment must be moment what? You don't write just moment. You must specify that moment. That moment is moment of what? Moment separaplastic for what? Not just like that. It's not clear. There's so many separaplastic. This is 10 plus 10 plastic. See that? 10 here, 10 here. You see that?
Yes.
Write it down. SP is what? Separaplastic. What are the moment there? Must be summation of force times distance. It's equal to F1 times D1 plus F2 times D2 plus F3 times D3. You must show where is F3, where is D3 there. And plus F4 times D4. And then you must write down there. F1 is equal to F4. F2 is equal to F3. D1 is equal to D4. D2 is equal to D3. Are you with me?
Yes.
Show that because you have calculate D1, but you haven't calculated D4. Show that this one and then this one. Only then you can write F1 times D1 plus F2 times D2 and then times 2 because symmetry. Okay? So what is the value there?
15733.3.
157
33.3.
33.3
0.3.
50,000, right?
Yes.
So before this is how many thousand?
13.
13.333 thousand. Now it's 15.733. So that is only 10 mm plastic. So the moment required to bend it this way. Bend means how much plastic that you want it to have that come from your experience. Are you with me, guys?
Yes.
10 mm also become plastic, but how much bending? That is come from your experience. When you work later on, you know how much plastic you want. From 1 mm until 49 mm. Which one is suitable for you? It's only from your experience, but must be separa plastic. They say you want, so this is the case for 17,000. So we can write it down. I write this one, okay? Just now, more 13,000, 13.333. Okay? 13.3 kilonewton. So 13.33 kilonewton. And then some more bigger moment separa plastic, we get 15.733. So this is 10 mm. 10 mm on top, 10 mm on the bottom. Total 20. That's why I write 10 plus 10. So this is 0 plus 0. But starting of plastic. Okay? So now let us make more. Let's say 40 mm plastic. This is 10 mm, right? So let's do some more diagram that is bigger than that. Let's say we want it to be like that. The diagram is like that. I want it to be let's say 30. 30 mm plastic, 20 there, 30 there. So this is plastic, this is elastic. So this is still elastic. 20 elastic and 30 plastic. So the diagram of the stress will become like what? You have to draw this confidently. 200, maintain until here. So the maintain until 200, 200. And then only then a straight line there. Just straight line there. So these are the stress diagram. So this stress diagram, sigma y 200, sigma y 200, sigma y 200, all the sigma y there. So from that diagram, draw the force arrow. So this stress here will act on that area, will become a force there. Okay? There will be another force there. Here. There must be a force here. F1. And then the triangle here, act on that area, there must be another force there. On the centroid of that, F2. And then the F3 there. And then F4 there, centroid of that square, F4. And then the distance from that centroid until that line here, we call it D1. From here to here, we call it D2. D3. D3. And then D4 there. Everybody clear on?
Clear.
Yeah, the same procedure. Only the size is changing. So we must guess. This must be higher than 15,000, right?
Yes.
Just now 10 mm, it is 15.7. So this must be higher than that. So how much higher? We can calculate easily. We can calculate easily. Okay, what is F1? Sigma average times area. So what is the average there? 200 plus 200 divided by 2. What are the area? 40 times 30. Got a value there. And then what is your D1? D1 there. So we know that's 20. This is 30. So how do we write the formula? 20 plus?
Half of 30.
Half of 30. So 35 there. Okay, what is F2? Same thing, sigma average times area. Yes, sigma average times area. So what do we have there? 2 is here, so 200 and 0. So 200 plus 0 divided by 2. Where is the area? The area is there. That area there. What is the area? 40 times 20. You got a value there. And what is your D2 there? Look at this. 20 there. So triangle there must be 2/3 of 20. Okay? And then we clarify. D3 is equal to D2, D4 is equal to D1, F3 is equal to F2, F4 is equal to F1. Everything is there. And then we calculate what is the moment separa plastic, not just MSP. Must know how much plastic there. 30 plus 30 plastic. So what is the value there? So F1 times D1 plus F2 times D2 and then times 2, symmetry. So what is the value there? What is F1 first? What is the value of F1 here?
240, then kilo.
Kilonewton. F2?
80 kilonewton.
Okay? What is the moment there?
$18.933 kilo Newton meter.
This is Newton. Newton, this Newton meter. Be careful, this moment, this is force. So this become higher and higher, right? So 30 become 18.933. This is 30 plus 30. Can you make higher and higher? Yes. So what is the maximum one? Maximum one, this 30 become what?
50.
This 30 become 50. All are plastic. This 30 also become 50. All are plastic. So what do you call it? This is called fully plastic. Are you with me?
Yes.
We can calculate the moment for fully plastic. So how is the diagram for fully plastic? So
Both
this is starting
way.
there. So this is a limit here. Moment fully plastic FP. This is moment separa plastic. A lot of things here. Not just one. This is two only. Example. This is a moment maximum elastic. Maximum elastic, fully plastic. So can we calculate it? Yes. How is the diagram? 200 there. All are 200. All maintain 200. You see that?
Yes.
All are 200, 200, 200, 200. Tensile. And then the other side here, all are 200 but compression. Compression, compression, compression. All are 200. 200 there, 200 there. 200 there, 200 there. So this is the maximum. We don't want it to happen. This is the total failure will happen this. So we have to calculate where is the limit. We don't want it to reach. Okay? So we can calculate it from the beginning before we do things. Must be higher than 13.3. Must be less than this. So why is that? So the fully plastic is much easier to calculate. Why? There's no triangle there. So F1 there. F1 there from 200 and 200 there. 200, 200. And then times that area. 200 times the area. There must be F2 there. So must be D1 there. Must be D2 there. Very easy. So what is F1? What is F1?
Sigma average times area.
So what's the average there? 200, 200. Divide by 2. And then what's the area? 40 times what?
50.
40 times 50. And then what's the value there? What is the D1 there? How do you decide that D1 there? Half of 50. 50 there must be half. Yeah? So, and then your F2 is equal to F1. And then your D2 is equal to D1 because symmetry. So, what is your moment? Moment fully plastic there. So what is F1 there, please? What is the value?
400 kilo. Newton.
400 kilonewton. And then this is 25 mm. And then for moment fully plastic, F1 times D1 plus F2 times D2. So must be F1 times D1 times 2. What is the value there? 400 kilonewton times 25 mm. Kilo and mm cancel out. So the answer must be Newton meter times 2. What's the value there?
20 kilonewton meter.
What's the value?
20 kilonewton meter.
20 kilonewton meter. So the maximum here is moment fully plastic is 20 kilonewton meter. So start from 13.3, 13.4 you can do the work. Start 14, 14.5, 15, 15.2, until 17, 16, 17, 18, 19, 19.1, 19.9 you still can work. But cannot be more higher than 20. Higher than 20, the material will collapse during the process of bending it. So now this is a point. Must be the load must be higher than that, must be lower than this. Are you with me?
Yes, doctor.
Very simple. So our exercise is just to calculate for this today. Just the cross section is simple, solid cross section. So next time we go a hollow cross section. How do we do that? It's just solid cross section, very easy. Okay, and only the triangle and square only. That's how. See that? So and then we decide. This is 30 and 30. 30 mm here and 30 mm. Easy for you to decide how much plastic that. Because say 10 mm on the top, 10 mm on the bottom. Sometimes doesn't say like that. Sometimes it's 20% of the surface is plastic. That means 80% is still elastic, right?
Yes.
So how do we decide that? Let's say this is 100. This is 40. So how do we draw that plastic? 20% plastic.
10 plus 10.
10 plus 10. Because 10 there and 10 there. So 10 there and 10 there. Easy. So the length is 80. Easy. But if the height is not 100, you have to do a simple mathematics. The height is also, let's say 40 only. So you say 20% is plastic. So how much?
4 plus 4.
4 plus 4.
4 plus 4.
10% is 4. Are you with me? The total is 40, right?
Yes.
So 10% is what?
4.
4. 10% is 4. 4 means 2 on the top, 2 on the bottom. That is 10%. This must be, from here to here must be 38. 2 mm there, 38 mm. So this is the definition of 10%. 20%, this must be 4 and 4. So bigger a little bit. This is bigger a little bit. 4 and 4, so this must be 36 mm. So this is 20%. So we must do the simple mathematics again. Are you with me, guys?
Yes.
So this is how you do the process. Okay, we do this for today. Okay, tomorrow we don't have class. The next class, how do we relate with loading? This is just cross section and we know that the material. The material yield what value and then we assume elastic plastic and we know the size. We can calculate, we can estimate the moment required. So the working moment must be higher than 13.3, must be less than 20. This is the rule. So we must understand this one first, we understand this one first. And then we calculate 10% or 20% somewhere here, up to us. 30% or 60% plastic is all here. All out can be used. Are you with me, guys?
Yes.
Okay, we stop for today, okay? And then we continue. Do some homework to calculate this cross section first. Okay, thank you very much. Assalamualaikum.